graphite-based anion exchange membrane for fuel cell application. This is all the introduction. Contents I'm going to explain today. That is Chapter 1, Introduction, Chapter 2, Experimental and its property, Chapter 3, Overall Conclusion and Future Work. So presently we are facing a very big problem, that is climate change. Even Korea and Asian countries is facing heavy flood, rain, cyclone, typhoon. It's all happening because of the climate change we are facing. If you see the United States NASA report, the global surface temperature is keep increasing because of the greenhouse effect, which is happening because of the carbon dioxide, which is nothing but the greenhouse gases we have been emitting because of the fossil fuel we are using, which is nothing but petrol, diesel, even coal. So these are all responsible for the global warming and climate change. We have been facing all these issues. So that is what now happening. So we need a solution which is environmental friendly. We need a sustainable energy which saves this earth. So how can we save this earth? So we are shifting to the sustainable energy. The clue is hydrogen. So hydrogen considered as one of the promising fuel. Even if you use it as a combustion or electrochemical conversion, it emits only water as a side product. There is no greenhouse gases. So that's why we have been shifting to the hydrogen economy. And South Korea, Jeonbuk is really contributing a lot for the hydrogen economy. So this is the report I found from the Jeonbuk government websites, which says the stance of South Korea in hydrogen economy. You can see the number of companies working on in the hydrogen production, utilization, and transportation. And this is the report which was published by the European Commission and Korea, which shows the roadmap of Korea in the hydrogen and applications. If you see in 2040, they almost aim for a very big amount of density using hydrogen, fuel cell vehicle, fuel cell bus. So first of all, you have to know what is the hydrogen fuel cell, how it works. So there are many types of fuel cell which is classified based on the electrolyte we are using and then the working conditions. So, even in Korea, in Jeonbuk National University, people are working in the solid oxide fuel cell, which needs a high temperature, which is almost 800 to 1000 degrees Celsius. But there are called low temperatures fuel cells. You can see in our university some Hyundai-based Nexo Cha, which is work based on the Suso changes, which is working based on the proton exchange membrane fuel cells. In this diagram shows how the fuel cell is working, which has anode, cathode, and electrolyte, which all these components have a separate advantage and disadvantages. In this one, membrane is the heart of fuel cell. The role of membrane is separate both electrode and anode and exchange ions from cathode to anode and anode to cathode. So my research is synthesizing, making an efficient electrolyte, because if you see the Tesla car, the Elon Musk Tesla car, which work based on the lithium-ion battery, sometimes this lithium-ion battery catches fire. How? That is because of the electrolyte being degraded. When it is degraded, anode and cathode form electrocircuit, and finally it catches fire. So our research is also making an efficient electrolyte which has a very strong physico-chemical stability. So this is the representation of proton exchange membrane fuel cell, anion exchange membrane fuel cells. So currently, whatever the fuel cell, so in Liu Changji bus, we have that work based on the first one, proton exchange membrane fuel cells. And the future, we will be having anion exchange membrane fuel cells. Both has advantage and disadvantages. Proton exchange membrane fuel cell needs platinum-based catalyst, which is highly cost. And also the electrolyte, which is predominantly used in PMFC, is naphthalene. You have heard about it. However, this naphthalene is not environmental friendly, and also it has many disadvantages in the physical chemical stability. However, in the cases of anion exchange membrane fuel cell, we don't need to use any platinum based catalyst. The total cost of fuel cell will be reduced, and also it is whatever the membrane we are preparing is a carbohydrate based. It contains mostly carbon and hydrogen and oxygen. There's no fluoride in it. However, in the PMFC there are fluoride, which is not environmental friendly. So this is the difference between proton exchange membrane and anion exchange membrane, as I have already explained. The anion exchange membrane is simple and low cost polymer. The working high oxygen reduction reaction is, the kinetics is very high compared to proton exchange membrane, because anion exchange membrane works in the alkaline medium, and it has a very flexibility when compared to proton exchange membrane fuel cells. Also, this pictorial representation explains in future in what are the applications this AEM electrolyte can be used. You can see direct methanol fuel cells, direct ammonia fuel cells, which is going to be predominant energy conversion device in future, and then CO2 electrolyzer. People have started working on it, and then water electrolyzer and hydrogen fuel cell. Even though anion exchange membrane have advantages over proton exchange membrane, there are still problems which can easily degrade by the alkaline OH minus, as shown here. There are different mechanisms have been proposed, that is SN2 reaction, Hoffman eliminations, and C2 eliminations. So by having all this mechanism, the membrane can easily degrade it. So as a researcher, what we do, we need to avoid all these problems. So that is how we design the electrolyte, and which is being then it will be used in the fuel cell application. So these are all the recent achievement, like literature, how people design to avoid all this problem to design an efficient anion exchange membrane. You can see the polybenzimidazole, polyvinyl benzyl chloride, polyphenylene oxide, and polyfluorine based, and polyaryl piperidinium. Polyaryl piperidinium is one of the best benchmark anion exchange membrane have been reported in the literatures, and people have been commercialized in the United States of America, especially in the Los Alamos laboratory in the Miguk. So by having all these ideas, these are all the ideas how we can make a very big, very best anion exchange membrane. You can see these are all the ideas. Let's say high electron cloud density, no electron withdrawing group, addition of fillers like graphene oxide or graphene nanofiber, cross-linking of polymer chains, avoid all the possibility of OH minus and attack, and having hydrophilic, hydrophobic microphase separation. If we do all these ideas, we can have a very big, very good anion exchange membrane electrolyte, and we can use it in the fuel cells. So by having all these ideas, I designed very novel anion exchange membrane, which is cross-linked between polyaryl piperidinium and polyether imide. And finally, you can see like so polyaryl piperidinium synthesis based on the Friedel-Crafts acylation, and then polyether imide prepared based on the chloromethylation. Finally, I made a membrane, as you can see in the figure, it's nothing but the electrolyte, anion exchange membrane electrolyte. This is the final structure, how it is going to be used in the anion exchange membrane fuel cell. So this is the basic NMR to find out whether I have prepared the successful the polymer or not. So whatever the peaks which were already reported in the literature is same as whatever I synthesis, so that I confirm I successfully made this polymer. And then these are all the basic physical studies of electrolyte. So we have to study about the morphology. We have to confirm there is no holes. Therefore, there is no crossover between the hydrogen and oxygen gases. So the FESM analysis confirmed there is no holes in the pinholes in the membrane. And also I confirmed the microphase separation. When there is a microphase separation, the ion mobility will be really good. If the ion mobility is good, it will have very good conductivity and then fuel cell performances. So all these AFM studies also confirm very good microphase separation. And then water uptake study explained how much of the water it can take, because water is a very good medium for the ion mobility. If a membrane has a good water uptake, it will have a good ion mobility and conductivity, and then fuel cell performances. So my study confirm it has a very good water uptake. And if you see the result, when I keep on adding the crosslink, at the PA, PTP 80% was reduced. The reason, when you have a more cross-linking, sometimes this cross-link can also stop the water uptake. So that might be the reason why the water uptake reduced after much more of the cross-linking. And then the TGA, which explain about, confirms about the thermal stability of a membrane, because we are running the fuel cell, whatever the Honda in Exo car has a fuel cell, there is a membrane, it will run at around 860 Celsius or Celsius. So sometimes the membrane will degrade because of the heat. So that's why I studied in the TGA. TGA shows up to even 100 degrees, 200 degrees Celsius. There is no mass changes. The initial mass change might be the just chocomole. So we don't have to worry about thermal stability in my invention. And then finally, contact angle and water uptake is almost same. If you have a very good contact angle, which means the electrolyte being a hydrophilicity, not hydrophobicity. And this is a very important picture I'm showing, which is going to be the feature for all the energy devices. That is nothing but the membrane electrode assembly. This kind of research is very famous in the European countries. They have started in a company, even Korea, like Doosan, they are also doing all this membrane electrode assembly. So this is how we make, first making the gas efficient electrode, anode and cathode, and the membrane, which is nothing but what I have prepared. We make a kind of a sandwich by using the punching machine. We make sandwich membrane electrode assembly. Finally, we assemble to the single cell to test the performance of fuel cell. So this is the final research. So what you are seeing is nothing but the electricity. So how much of the membrane electrode assembly produced the electricity? So this is just a single cell. The surface area is around 2.5 centimeter, very small. 2.5 centimeter squared membrane electrode assembly have produced around 200 milliwatt per centimeter square. So this is same as like whatever the field Suso in Liu Chenji cha we have. So that surface area will be very bigger, and they have a stack, very big stack, that will produce the electricity around 10 watt or 20 watt. So since it is a single cells, it shows up to around 200 milliwatt centimeter squared. As you can see, the PA, which doesn't have any cross-linking, shows the power density around 150. However, with the cross-link around 60% shows the improved the electricity production, which says gives hope for my research. So here is the conclusions. So I have confirmed by doing cross-link with the polyethylamide and PAP, we can produce very good electrolyte, which can be used in the Suso Indio Chanji and water mul electrolyzer, even CO2 electrolyzer, many more applications. So that's what I have found out. I have submitted this paper to the American Chemical Society ACS Sustainable Chemistry and Engineering. Right now it is under review. And future work. So recently I have invented this device along with my professor Jeonbuk. We proposed this idea. For example, even hydrogen is going to be a green fuel. In future, the hydrogen source is going to be very big problem, because handling hydrogen is not easy. It's the safety is, we have concern about the safety. So in future, we have to try with different fuel. So what I have proposed is just mul. By having mul, you can run your car. This is a proposal. It's already started. People name it as a unitized regenerative fuel cell. Just pass mul over there, H2O, that will split hydrogen and oxygen, and then insert the hydrogen and oxygen into the fuel cell. Now you produce electricity. So this is the future work. I have been working on it. An acknowledgement, I thank my lab members, my cousin Jin and others. Thank you.